So good afternoon, everybody. Yeah, I'll take some time to wait for the last one to take a seat. So welcome to this session about machine learning and side channel analysis. This is the first out of 2 sessions about this topic. We have 3 talks that will be given in this session. So the first topic tells us, don't learn what you already know. It's about scheme-aware modeling for profiling side channel analysis against masking. And the talk will be given by Loïc Mazur. Loïc, the floor is yours.
Thanks, Eleonora, for the introduction. So this is a joint work with Valence and Maxime from CEA. Valence is now in Ninja Lab. And this is also a joint work with François-Xavier Standard from UCL Crypto Group. Okay, so a bit of context about side channel and machine learning and masking. So yeah, most of you know the framework of side channel analysis. The idea is to try to leverage some physical traces that depend on some public message and on some key chunk of a secret key in order to guess some small piece of a secret key in a divide and conquer approach. And this is important to take into account because such kind of attacks are linear with the size of a key, whereas the usual black box script analysis is typically exponential with the size of the key. But to protect against such analysis, we have masking. The idea is to replace the processing of any computation involving secrets by some corresponding share according to a given secret sharing scheme. So let's say take an additive secret sharing scheme where your secret is replaced by the sum of some d+1 shares. And instead of processing the secret directly, you will process the d+1 shares instead. And this will be these d+1 shares that will leak instead of the secret directly. And how can an adversary recover some information about the secret? Well, he or she can turn some small piece of a trace into some scores, probability distributions vectors, giving some scores for each possible value of the shares, and then to recombine these probability distributions according to a convolution product into a probability distribution about the secret. There is no way to do other. This is the optimal way to recover some information about the secret. Okay, but now how to convert this small piece of trace into, sorry, I made the mistake. Thanks. How to convert this small piece of trace into score vectors? Well, we can use machine learning and more precisely deep learning. This is exactly the aim of deep learning, which is a function that will turn some leakage into some score vectors. Deep learning model is just a set of functions, a function which is made of some elementary functions that are parametric, which depend on some parameters that needed to be tweaked in order to fit the ground truth. And this fitting, we will see that it can be done during the profiling phase. Typically, how does profiling phase happen? You assume that you have a clone device on which you have a full control, or at least some power, to be able to communicate with this device, and more precisely, to be able to know or to choose the value of the secret key and of the plain text that are used to compute some elementary computation that will leak. And that allows you to draw some score vector here, which is the exact prediction we would like our model to give. On the other hand, you will measure the trace at the oscilloscope, for example, and you plug this trace into the model you want to fit. And this model will return you initially some random score vectors. And your goal is to make this score vector fit with the expected prediction. And to do that, you will compute a loss function, which quantifies the dissimilarity between the return score vector and the expected score vector. And ultimately, this loss function depends on the underlying parameters of your model. And the goal is to minimize this loss function with respect to the parameters of your model with gradient descent. This is the only thing you need to remember from this slide. We will consider only gradient descent. And typically, what we are used to see in the deep learning papers in such analysis is that the authors consider what we call a non-informed adversary, which means that we assume the adversary to have no knowledge on the random shares used to generate the masking scheme. We only assume to know the key and the plain text. But we could also consider what we call the worst case adversary, where in addition, we also assume that the adversary has a full control over the randomness generation of your device. And in particular, the adversary can know during the profiling phase the value of the random shares. And what is the difference between both approaches? Well, if you are in the latter one, which we could call a natural way, you can simply divide, you can apply an extra divide and conquer approach into your profiling phase. Namely that you will split your overall model into some sub-models. Each of these sub-models will aim to target, to predict one share at a time. And once you have done the training for all your sub-model, you can recombine them during the attack phase with the convolution product here. Okay, and if you don't know the randomness during the profiling phase, well, you can just assume that your model is just an overall model that will take into as inputs all the leakages corresponding to all the shares, and then to aggregate them and to optimize the parameters with gradient descent in order to minimize the overall loss function depending on the secret. Okay. So let's look at what happens. The problem is that when you consider an uninformed adversary, you can see here what we call the learning curves. So the idea is that you measure the amount of information that your model can extract depending on the amount of profiling traces you would acquire at the oscilloscope. And what we can see is that in the worst case, you have a very fast convergence, whereas in the uninformed case adversary, you have a much slower convergence by several orders of magnitude. Okay, so on the one hand, we would like an adversary that is kind of realistic, but on the other hand, we would like an adversary that can leverage all the information he has into account. The only problem is that during an evaluation, typically, some designers may be tempted to restrict the access to the randomness generation so that the evaluator is restricted in its power and that the evaluation outcomes are artificially lowered. And we would like to avoid that. And an evaluator could wonder, okay, how can we leverage the knowledge of a masking scheme without having necessarily to rely on the knowledge of the random shares? And can we do that? And the answer is yes. And this is what we call the scheme-aware approach. So the idea is pretty simple. We do not claim many things revolutionary. The idea is to transfer this computation of a convolution product from the attack phase to the profiling phase. And how do we do that? Well, we keep our submodels here that are that aim to take into as inputs only some piece of shares depending on one share specifically. And we'll combine here before computing the loss function, and then we train jointly these models according to the overall loss function. And how can we do that? Well, we need to implement the backpropagation algorithm necessarily to run the gradient descent inside this discrete convolution layer, which is different from the convolution layer of convolutional neural networks. Okay, so this is not very hard because convolution is just a multilinear mapping. So this is the gradient is easily implemented, and we made an implementation on PyTorch. I'm aware maybe that if you attended the RAM session yesterday, one of the runner-ups of the CHES CTF implemented a TensorFlow version of this layer. Okay. So let's look at the outcomes in simulated experiments, for example. So we can still see the convergence, the learning curves, which is, I will call, the amount of information you can extract depending on the number of profiling traces you may have at your disposal. Yes, you have the fastest convergence for the worst case adversary, which is the most powerful adversary naturally. You have still the worst convergence for the uninformed adversary, and you have a trade-off convergence here for our scheme-aware adversary. And what is interesting is that we still have some gains by at least one order of magnitude, and this regardless of the level of SNR. So this is just on experiments over Hamming weight plus Gaussian noise, the typical simulation framework. Let's see what happens now on experimental data. So you have here the two versions of the ASCAD V1 dataset, which is a first order Boolean masking. We can see similar results where we have intermediate results between the worst case adversary and the uninformed adversary. We also extend the computation over the Spook dataset, which took part of the CHES 2020 CTF. And here, this is a Boolean masking with 3 shares, only 2 bits as a target, but 3 shares. So yes, the convolution product, it can be easily extended to higher orders. Well, actually, can it be completely extended? This is the question we were asking. Because now we have some good results and we wanted to extend our results over the recent ASCAD V2 dataset. ASCAD V2 is an AES protected with affine masking. So the first thing we did was to run some simulations on the affine masking. You can implement this discrete convolution layer with affine masking. This is a bit tricky, but this can be done fairly well. We ran some simulations and we could see that we had, so this is the loss function depending on the number of iterations of your gradient descent. And what we can see is that we have almost as good results as in the worst case. But whereas for the uninformed adversary here, which is a simple MLP, we could realize that, yeah, we have this kind of plateau and then, yeah, nothing successful happened because we are not able to learn because we are not below the threshold of 8 bits, which is the entropy of the target. So we are not able to reduce the entropy. Okay. So we had this plateau, but we could still learn. And then we try to apply this attack on the ASCAD V2 dataset directly on the public dataset, and then we failed. So this is a bit embarrassing, but why did we fail? Well, this is due probably to what we call the plateau effect. And this plateau effect, I will argue in the next few slides that this is the elephant in the room currently in machine learning applied to side channel analysis. And we should take this problem into consideration. So why? Well, let me show you some few examples from the recent literature. So you have here an extract from the nice paper of Timo at CHES 19, where he targets some first order leakage and here some second order. And what you can observe is that you have here a plateau. So this is depending on the number of iterations on the x-axis. And what you can observe is that you have a slightly longer plateau. The observation is even more obvious here on this figure from a recent paper of my co-author Valence Cristiani, recently out at JOC, where you have here first order masking as a target on simulations, and here a second order. And what you can see is that the length of the plateau seems to be much longer when you increase the order of masking. You have also some other examples. So this is Pera and Pitchek at SAC20 on the ASCAD dataset. So you can also observe this plateau, and another paper from CHES 21 from Lu et al. Where they were considering another framework where they wanted to target the whole traces, the raw traces, but you can still observe some plateau. So, okay, we have this pervasive phenomenon and nobody is talking about that. So what can we say about that? Well, first we run some simulations, and in a simulated framework where we assume each share to leak the Hamming weight, it is kind of noise-free. Yes, it is noise-free. We are in a simulation framework because in such a case, we are able to generate an exhaustive data set without having, we can, generate the overall leakage distribution without having to generate the overall distribution of the shares, so which spares a lot of data. And since if you have attended my colleague Torben talk yesterday, you would be aware that in such a case, noise-free with Hamming weight, regardless of the masking order, we will still leak at least 1 bit on the secret. So we can run the experiments and increase the number of shares while still having something fairly comparable from one order to another. And what we could observe here is to measure the length of the plateau, and we can see that it is almost exponential on our schema-aware model, and not really exponential, but at least super polynomial in the uninformed case, which is the classical black box way to run deep learning attacks. So yeah, it seems to be a problem that we cannot avoid, especially if in the next few years, we will have to target some implementations with much higher order. Okay, so can we find a theoretical explanation to that? There exists a few literature about that. In particular, I found this paper from ICML by Shalev Schwartz, Shamir, and Shama. This is not the same Shamir. So assume that you have you have a leakage on D shares, and each piece of leakage for each share can be seen as a Gaussian distribution of dimensionality P. So, and this is only on a bit level. So you have half of your space, which corresponds to the bit 0, and half of the space that corresponds to the bit 1. So you only need, as an evaluator, as your model, to guess which is the decision surface, which is represented here by the hyperplane U. And assume that this is the same decision surface for every bit. Well, what this theorem says is that if you run in a model either in an uninformed case or in a schema-aware case, so everything which is not worst case, then you have some upper bound on the variance of the direction of a gradient, which is upper bounded by something which is exponential in the number of shares. So the interpretation of this theorem is that regardless of your leakage model on this bit size and this monobit simulation, well, the gradient will almost take the same direction, which is a bit uncomfortable because, yeah, this means that the gradient carries pretty much no information about what you are trying to learn. Okay, so as a conclusion, well, it seems that if we want to tackle higher order masking with deep learning, the outcomes remain unclear. Can we directly conclude that gradient descent is not suitable at all for such cases? Well, we have some evidences, but it needs to be consolidated by future research. And if so, we have another question, uncomfortable question, is that is there any efficient surrogate to gradient descent? If so, then that means that all our current evaluators and all the current state of the art would be completely outdated and outperformed in the next few years. Otherwise, if there is no efficient surrogate to gradient descent, well, could we make a reduction of this problem to some hard learning problem? Well, this is an open question yet. But then that would mean that there is an interesting gap between the worst case approach that the academic world considers in the masking proofs, for example, and the concrete approach that evaluators do in evaluation labs. But my point here is that regardless of the answer, this is worth investigating. And if you're interested in this topic, I would really encourage you to get in touch with me or get in touch with our labs because yeah, I would really like to work in this direction in the next few years. And I may have some open positions soon. So if you're interested, just let me know. Thanks.
Thank you very much, Loïc. So there is time for questions, and you actually already received a question from the chat. Can we expect to have the schema-aware approach almost as efficient as the worst case? What are the challenges? Sorry, well, the question has been removed because of the last slide that already answered.
Okay. So you have the answer of the last slide. This is the $1 million question to me.
Okay. Are there any questions from the audience? Yes, over there.
Thanks a lot. Thanks a lot, Loïc, for the presentation.
You're welcome.
So I was just wondering, so in the first part of the presentation, you mentioned that you do schema-aware training, but then does the plateau effect that you explained in the second part applies to the first part? So do you, yeah.
You mean applying the plateau effect on what?
Okay, so does this effect that you observe on the rest of the literature, which is doing no schema-aware inference, does this plateau effect also apply to the schema-aware learning?
Yes, it applies to uninformed adversary, schema-aware adversary. So this is this picture is a bit misleading because it seems to also apply to worst case, but what I argue, and from my past experience and what this theorem argues, is that it does not cover worst case adversaries. Because worst case adversaries, you assume that you only target some first order, some shares leaking at the first order. So it should be fairly easy from our common experience. It can be targeted with Gaussian templates or MLPs easy. Does that answer your question?
Yeah, perfectly. Thanks.
So it seems to me that we had another question just here. Yeah.
So thank you for the presentation. A quick question. Which hardware did you test this on?
So far, no hardware. I guess that in hardware, actually, the level of noise would be very hard. So that maybe probably deep learning, whether it is schema-aware or uninformed, is not necessarily the best option. Maybe I'm wrong, but yeah, this topic mostly targets implicitly, I admit, software cases. But there would be no limitation, I would say, to apply it to hardware. Only experience would confirm that.
We have still a few time for questions. There is one right there at the end of the room, please.
Thank you for the talk. I have a question. You train your model jointly on the secret, and if I want to use this model on like masking on PQC scheme, whether secret like on a small range of the group, then do you think does it affect the conversion of the model?
So thanks for the question. Actually, I tried some experiments on arithmetic masking, which would be the natural way to mask in PQC. The performances are a bit different than in Boolean masking, less impressive, I would say. But this is still fairly extendable regardless of the prior distribution of a secret.
Thank you. If there is any small question, we still have time. Oh, yes.
Hi, thanks for the presentation. I was wondering what affects this plateau effect, and do you know if the leakage function, its bijectivity, has effect on the length of the plateau and also the noise? Because I don't see it in this very complicated formula?
So I think there is a trade-off, because if your leakage model is bijective, then you will face a huge problem with optimization. On the other hand, if your leakage model is not bijective, then maybe the optimization would be less complicated, but on the other hand, you would extract much less information. So yeah, you gain on one side and you lose on the other, and this is not clear yet. But how much bijectivity is needed to characterize this difficulty? Well, I don't really know. Perhaps there are also some non-bijective leakage models that also face this problem.
Okay, the time is over. We can thank Loïc again. This is the pointer you can find. Okay, so the next talk is about peek into the black box, interpretable neural network using set equation in side channel analysis. And the talk will be given by Trevor Yap.
Thank you for the introduction. Yeah. Yes, so I'm Trevor, and today I'm going to present my work. This is a joint work with Adrian Benamira, Shivam Basin, and Thomas Perring from Nanyang Technological University, Singapore. So this is the outline of my talk. I'm going to give an overview of what side channel analysis and deep learning is, followed by the architecture that actually we use, known as the truth table deep convolution neural network, also known as TTDCNN. And this neural network is actually proposed by previous work, and we try to use it for side channel analysis. So this work, this TTDCNN actually can able to convert the weights into set equation for interpretation. Therefore, we actually propose methodology to analyze these set equations, and then we apply it to simulated traces and propose a type of TTDCN known as TTSCA small. And then we try to scale it up to real traces and propose another type of DCNN called TTSCA big. Then we end off with some conclusion. So an overview. So suppose side channel, I'm quite sure all of you know what side channel is. So suppose you have a cryptographic implementation and you want to attack the implementation, but not on the algorithm itself, but the physical leakage, such as power consumption of electromagnetic wave, also known as traces. Analyzing these traces allow us to actually recover the secret key. So a type of side channel analysis is actually what we know as profiling attack. So as just now the previous talk mentioned, we actually has two devices, device 1 and device 2. So device 1, the evaluator or adversary will be able to know what is the key or could even manipulate the key. Then you train a model, and using this trained model, you attack the second device, known as the target device, where you do not know what is the key. Then you use this trained model together with a metric known as Gaussian entropy or success rate. You can actually recover the secret key. So in our work, we actually only look into Gaussian entropy or the mean rank of the secret key. So if it is converges into 0, then we recover the secret key. So a type of model that has been used recently is called the deep neural network. And this slide we actually show is a convolution neural network with convolution layers and pooling layers followed by fully connected layers. So you just place this into the profiling framework and train it and attack. So why do we actually want to use this deep neural network based side channel? It's because it has been shown in practical settings with countermeasures and with noise, we are actually able to use significantly lesser traces to attack compared to classical side channel analysis like template attack. And it requires little to actually no pre-processing needed, unlike the classical attack, where it requires tedious pre-processing to remove desynchronization and to obtain the point of interest. So the disadvantage of DNN is that it is actually a black box tool, and we have far too many hyperparameters to tune compared to classical side channel analysis technique. So we do not actually know which architecture to use, although currently there are a lot of auto-tune methods to find this hyperparameter, but mostly are time-consuming. And furthermore, evaluator actually wants to help developer to localize and understand where the vulnerability comes from so that we can actually remove or at least reduce it. But the problem is there are actually lesser work in interpretability and explainability of deep neural network within side channel analysis. So what we want to do is to explore what the neural network is learning in side channel analysis, but explainability or interpretability it has many sides to it, and it has many definitions for different people. So in our case, we're going to propose a neural network that is easy to interpret. So we want to note that the proposed architecture is actually not for efficiency, it's only for interpretability. So we use this TT-DCNN. So what is it? So suppose we have a convolution of 2 layers. Layer 1 has kernel size 4. This means that this 4 points over here is multiplied by a weight to give you this, multiplied by another weight give you this thing, and then this, and so forth. Then in the next, you have this 4 points because it's strike 2, so you jump 2 steps. It gives you this point, bottom, and then this with different weights. Then in the second layer, I have a kernel size of 2 with strike 2. This means these 8 points over here in the blue box would multiply with a weight to obtain the point at the last output. Overall, it means that 6 points at the front of the input is used to calculate the first output of the last layer. So this 6 points, we call it a patch, and the number of points of the patch is called the patch size. So if we binarize the input and the output, now we are able to create a truth table by enumerating all possible inputs. So this truth table is actually can be converted into set equation for interpretation. We know that now the weights can actually be removed, and we just use a truth table to actually calculate this. So here, we convert the truth table into the set equation known as disjunctive normal form DNF using the Cream-McCluskey algorithm, and we apply it into side channel analysis. So by applying it into side channel analysis, we are able to pinpoint to the location of the point of interest for the leakages and actually see that the neural network is able to combine the leakages. So methodology. However, we found out that most of the disjuncts in the DNF are actually unnecessary for key recovery. And we want to know which of these disjuncts or literals are actually important for key recovery. So we propose 3 heuristics. Number 1, we sieve it based on the size of the disjuncts. So let's say you have a disjunct. The size of the disjunct is defined as the number of literals within it. So in this example over here, it has 4 literals. So we call it a disjunct of size 4. Then secondly, we actually separate the disjunct based on what we call combination of literals. So the combination of literals is a set of disjuncts. Let's say, for example, here, a combination of literals of x1, x3, x5, x6 is actually all the disjuncts with these 4 literals, regardless whether it has a NOT gate or not. Then we trim it based on the literals. And if we trim the literals, let's say x3 from the disjuncts, then we just simply remove this x3 from the disjuncts. So what's the goal of our plan? Our goal is actually to find the most miniature set of rules or set equations that the neural network actually needs for key recovery. So we apply it to the simulated trace first. So we propose TT-SCA small because we found out that the neural network actually overfits very fast due to it being a perfect world. So we requires to actually use this heaviside function which binarize, also known as Bing-Add, over here in between convolution 2 and 3. And then after training, we will put another Bing-Add at the end of this convolution layer 3. Then the green part over here, we will convert it into set equation for interpretation. So as was given by the previous talk, masking. So suppose we have a masking order D. That means we have D plus 1 leakage point, L1 to LD plus 1. Then the secret variable Z is actually a function of G of this L1 to LD plus 1. So a common function of G is actually what we know as a Boolean masking, using the Boolean XOR of each leakage point, which is what we're going to consider in this work. And the simulated trace that we use is, the visualization is as shown below, with M1 and L being the leakage point. And when we XOR them together, we will recover the secret variable. The orange color box, the blue color box, and the green color box actually shows the patch of what the neural network sees in each time step. So in the second time step, which is the blue box, we see that the neural network sees M1 and L at the same time. So we will expect that it will recover the literals X1 and X6. So we want to see whether it does. So we use our heuristic and we see based on the size, and we see that indeed the smaller size we got is the size 2, with the min rank going down to 0, which is the orange line over here. Then what are these disjuncts inside? We see that they are actually of this form, X1 and indeed X6. So we want to make sure that they really use X1 and X6. So we try to trim it individually. And when we trim it individually, the Gaussian entropy increases and no longer converges to 0. This means that these both literals are important to the neural network. So this means that the TT-SCA small can actually pinpoint the leakage in a black box setting and still use them to actually recover the key. Then we obtain a similar result for other masking order 0, order 2, and order 3. In this table, we actually shows the disjuncts, an example of the disjuncts that has been recovered. Then we explore whether the TT-SCA small is able to recover the key using exploitable leakages. And suppose now we have a masking order 3. So it means I need 4 leakage point to recover the key. But if we consider an existence of one more leak A over here, if it means that it becomes a masking order 2, and we see that the neural network indeed able to use this exploitable leakage, because we find that using our heuristic is able to detect this exploitable leakage of X1, X2, and X6 to recover the key. Then we further investigate. Let's say now I am masking order 1. I have 2 points. Okay, 2 points. If I put them far apart, because previously it was in the same patch, now I put them far apart, could the neural network actually still recover the key? And we find that it is not possible to recover the key. The Gaussian entropy does not converge to 0. This means that at any one point, both the leakage point needs to lie within the same patch for the TT-SCA small to recover the key. So this comes to where we want to scale it up to real traces. Of course, the most obvious way is to apply TT-SCA small onto longer traces to actually increase its patch size. Is to just increase its patch size. But then when we try to use the Quine-McCluskey algorithm, right, we are actually solving an NP-complete problem of simplifying set equations. This means my patch size cannot be more than 12. So with this limitation of this patch size, it becomes harder for us to apply it onto like practical trace with thousands and millions of actually trace of our sample points. So one way is to increase the learning capacity of TT-DCNN, which was proposed by its original work in what we call the where he introduced what we call the LTT block, learning truth table block, by introducing the extra convolution layer of kernel size 1. But for us, we actually consider a pre-processing block also with this convolution 1D, 1 batch norm and average pool. This is the pre-processing block over here. Then using this pre-processing block, we can actually reduce the patch size to less than or equal to 12. Then we convert the LTT block over here to set equation for interpretation. So when we use the pre-processing block, the literals no longer become one sample. The literals now actually is a window of sample points. So in the SCAP fix here, we use each literals as 100 sample points. So we do our heuristic and we apply and see that for disjunct of size 4, it is actually the smallest size with gassing entropy equal to 0. However, when we see the number of disjuncts, there is actually a lot more. So we requires us to cut it down. So we use the second approach to see based on the combination of literates. So we use an algorithm in our paper to obtain what we call critical combination of literates, also known as the combination of literates that are relevant for key recovery. So this is the list. Then we trim it and we obtain X1, X2, X5, X6 as the most important literates for key recovery. So what are these literates meant for? If we look at CPA, which is a white box setting, the neural network is able to pinpoint the leakage point of all the masking of the leakage of those mask and the mask data. So this means that TT-SCA-bit is able to use the point of interest to retrieve the key in a black box setting. So we want to note that each training is actually non-deterministic, and this means that each neural network has its own slightly different interpretation. So in our case, we found out that in the best case, it's actually able to recover only with this filter 66, which actually corresponds to one XOR gate. And this XOR gate actually corresponds to the Boolean masking. And this Boolean masking over here is actually the X1 and X5, which is the leakage of the mask and the mask data. So overall, in this best case, we found that the TT-SCA-bit is able to retrieve the key with just only one pre-processing block, one XOR gate, and one linear regression. So here we present our result for SCAP fix. We validate our approach on two other public data set, SCAP random and also AES HD extended. So conclusion, we propose two types of architecture based on TT-DCNN, known as TT-SCA small and TT-SCA big for side channel analysis. Then we propose heuristic to actually analyze these set equations. And we show that in TT-SCA small, it actually able to detect bad implementation. And lastly, we show that both proposed architecture able to pinpoint point of interest and combine the leakage found. In the best case, we are able to find the masking function. This comes to the end of my talk. Thank you.
So thank you for the talk. We have time for questions. Are there any questions? Yes, right there.
Thank you for your talk. So in the last result, you found that the expression is just XOR.
Yes.
While initially you were looking for formulas using AND and OR gates. So maybe it would be better to start by looking at XOR gates, and because you're dealing with masking. So why AND and OR gates, not just XOR gates?
I think because we only use the truth table, and then from the truth table, the library that we use, we only change it into a DNF and CNF. That's why. But I think it's interesting to look into that also.
Okay, thank you.
Are there any other questions? Well, by that time, I'll ask you a small one. Your methodology does not work with desynchronized traces. So at the time you wrote your paper, you left it for future works. I was just wondering if today you have some intuition about how can you improve this methodology to deal with desynchronized data?
So actually, I try on desynchronized, and although it kind of worked, now the gassing entropy now goes to 0, but I found out that it actually uses every single point. So it becomes, I don't really know what I can actually interpret from there. So I will leave it as a future work also, like, yeah.
Thank you. So last chance. Are there any questions? Oh, yes. One at the end, please. Just now behind you, sorry. There was a question before at the end of the room, please. There.
Thank you for the talk. I'm curious if it's naturally extend to arithmetic masking.
we didn't really try it because on its own XOR is really difficult. So
Yeah.
that's why. But it could be a future work to look into that also.
Okay, thank you.
So there was one more question right there.
I just was wondering, you said on one slide that the interpretation varies depending on each training. I assume it's because of the randomness during the initialization of the neural network. Did you look into that when you fixed the randomness during initialization of the weights? I mean, it should be the same every training then. So did you fix the randomness?
Yeah,
or?
so indeed, so I didn't really fix the thing but partly also because the heuristic that we propose are actually kind of random on its own, especially the algorithm one that we actually proposed. It has some kind of randomness that is embedded into it. So therefore, we know that there is like different set of miniature set of rules. So we just somehow managed to find that set of miniature rules.
Oh, okay.
So you have one question from the chat. How the method compares to previous interpretation methods proposed in the literature? How your method compares with other interpretation methods proposed in the literature, I guess, for example, with gradient visualization or, I don't know,
yes,
CVA that will be presented just next.
So in this case, the in gradient visualization and all those are mostly what we call explainability methods. But in our method, we actually is a interpretability method. So we exactly know what the neural network is looking at, but the gradient visualization, you only look at only one sample or a bunch of sample, and you just know that the neural network sees these are the set of important points for this set. But in this case, we can generalize it to every single trace that we never even tested it because it's set equations.
Okay, and you also may tell us something about a comparison with convolutional variational autoencoders that will be presented just next. But I know that you, you know, convolutional variational autoencoders. I know that you could comment about it because you speak about that in your paper. So I don't know if the person in the chat wanted to ask for some other methods in proposed in literature. So maybe if we can, but I don't know if you can compare with the CVA.
Oh, I think it's just different way of looking. Because for my case, I look at the discriminative model itself. So instead of looking at other models, because discriminative models itself is the model that most at that time most of the neural network is based on. That's why.
Yeah. Okay, so another point of view. We still have time for questions if there are any more.
Yeah. Can I have a question? You said that you focused on interpretability here. So do you have some comparison to the network optimized for like effectiveness or results?
Compare with, sorry?
If you compare your neural network with the one which is optimized for power.
Oh, so this work is just to try to peek into it to look at how the neural network actually works. It has lower efficiency compared to the optimized version or the black box one. So yeah, so this is just a work to make it easy for us to understand what the neural network is actually looking at. So we have some intuition for the black box neural network.
Okay, so it's a huge difference, you say?
In
efficiency.
In terms of efficiency, yes, because for the ASHD, right, we need to use extended, but the neural network black box just uses ASHD, so it requires lesser trace to attack.
Okay, thank you.
Maybe one last question? No, so we can thank Trevor again.
Thank you.
Thank you very much. So the next talk is about information theory-based evolution of neural networks for side channel analysis. Slides are there. So the talk will be given by Seba, also known as Fatema Genji.
Hello, everyone. Thank you for joining us in this session. Oh, I think I pressed a button unintentionally. I have the privilege to present this work. That's a collaborative work, and my mentee Robin Acharya couldn't manage to attend. Therefore, I have the chance. Till now, it should be clear to us why we are using machine learning and, in special cases, deep learning for side channel analysis. We know that what do we know about it? Who knows what we are doing with all those neural networks?
And see that they are very professional. They stop the timer. So don't worry, the timer is stopped. Technical problems.
Good to go? Shall I? Okay. So I was saying that now the motivation is quite clear to all of us for what reason we are using deep neural networks. We know that they can achieve great performance compared to the statistical traditional methods. We know that they can be applied to protected, unprotected targets. And perhaps applying neural network can be seen as a step towards making the side channel analysis a bit more automated. But of course, it comes at a price, and the cost is attributed by finding the right network and then find the right set of hyperparameter for that network. We have seen many different neural network applied in this scenario. We have seen convolutional neural network, multi-layer perceptrons. They are both doing fine with different general features that you can see on this slide, but per application, per dataset that you may consider, this table might be checked. This is just a general overview, but we know that at least for tuning hyperparameters, multi-layer perceptrons could be quite easier to tackle. Let's focus on that and see what we know, how we begin. Most of the time, we are relying on the knowledge of the experts, just telling us what network should be chosen. We do some trial and error to find the right network, but is it the only way to do it? Of course not. There is one concept developed in the machine learning field of study to tackle this problem, and it's called neural architectural search. You have been, if you have looked at the literature applying neural network for side channel analysis, you have seen many flavors of these. For instance, we have seen that the number of layers is chosen by the network itself just by giving the, let's say, the maximum number of layers that is possible. Or we have seen other cases where the network itself tries to find out what function to be involved in what layer. As an example, if you're talking about convolutional neural network, what kind of filter size should be chosen? What are the loss functions to think of? And one can go even one step further and try to tune the hyperparameters. That means the number of neurons in one layer, when to stop the algorithm, and so on. Those are all different levels of NAS, neural architecture search. So different layers, different possibilities. But the most advanced way developed in the concept of NAS is trying to make the connections between the nodes we are talking about multi-layer perceptrons for the time, just for the simplicity, try to find the branches, how they should be connected to one another. Just compare these two neural network, and you will see that the one just at the bottom of the slide has some irregular behavior, some irregular connections. And what we have observed in that, so far, all those flavors at the bottom of this hierarchy have been explored in the side channel analysis related literature in different terms that you can see on the slide. And what I'm going to show you today is how the most advanced type of neural architecture search can be applied to side channel analysis problem. And let's agree on this question for the moment. Assume that I have a very small neural network. I want to tweak the connections between the nodes and find the most appropriate one to be applied to traces in the hope that I can attack the targets efficiently. And for that problem, we have a solution developed in machine learning, and that is called neuroevolution of augmenting topologies. That means just like living creature, we start with very simple genome, and this genome will evolve and make a new creature. And how this is possible? At the first stage, I said before, randomly we create very small neural networks. And then in the next step, so let me also tell you that even when we are creating these simple creature neural networks, at the first stage, the layers are very irregular compared to usual multi-layer perceptrons, for instance. Then we go to the next step when we have evolutionary algorithms governing the algorithm, trying to help us build new creatures, new neural networks. For instance, the crossover mechanism can be used to just exchange nodes and connection between two neural networks. We have mutation at that level. We can add nodes, we can add connection to the previous generation of neural network. And then we end up having new population. That means this new population has many neural networks. Each neural network is called a genome, and a set of neural network with a special feature is called a species. Okay, just keep this terminology in mind. We will get back to it. So many neural networks have been evolved together. All these can just run and run and run, and I don't know when to stop it. And you see those blocks in red? Those are the bottlenecks of the original neat algorithm. We don't know when to stop it. We don't know from which species, which genome should be chosen. There are some heuristics, but we have been trying to answer this question. Are all the neural networks that we have been evolving are good enough to be taken into account? To answer this question, we have used notions borrowed from information theory. And it is very intuitive. When do I stop learning? If I want to do a task, when can I say that I have learned enough? As soon as I would say I have gained information from the, let's say, ground truths for the inputs that I'm getting from time to time, I would say I have learned enough. I can now take care of the next task that I have not seen before. That is exactly the concept that we are using in InfoNet. That is the new algorithm that we are creating together. And for that, we say, assume that I have two neural networks. I want to know which one is better. For that, I just compare the mutual information at the last level the mutual information between the labels and the inputs given to those neural networks. That is the mutual information. And then I just compare how these two have learned, how much information have been extracted by each of those neural networks. And these criteria is applied to, first of all, select which neural network from which species should be chosen. There are many, actually, when you evolve all these neural networks together, there are many of them coming with the same fitness level, but we have observed that they are not as good as, I mean, the level of learning is not the same for different neural network. And we used CMI to just find the best genome, best neural network from the possible species. And the next point is that when can I stop evolving the neural networks? Just comparing what I had in previous generation and what I have achieved in the next generation, comparing the mutual information again, it is possible to say that's time to stop it. The neural network has learned enough to tackle the problem now. Okay, till now we have been just improving the needs, but what about side channel analysis? That's the next part of the title of the paper. In fact, one cannot use neat plug and play to be used for side channel analysis. Why? Because neat by itself has been created to tackle binary problems. For problems with multi-class, it is not applicable. It cannot just work on those problems. That is the next novel part of the approach, where we train InfoNeat now creators on each class, and finally we take the knowledge of all those neurons together, we stack them and create one model that contains all these small neural networks coming together. So that is the concept of stacking, and how one versus all training can be used to create one stacked model. All these being said, we can now take a look at some of the results. We are not going to go through all the results in the paper, but just some examples. So first of all, we have applied InfoNeat against 3 datasets, ASCAT fixed and ASCAT variable keys, and ASHD. Why these datasets have been chosen? Because they are more or less serving as our benchmark. If I want to compare my algorithm to other algorithms, I should just find what dataset has been used by many groups to have a better understanding of the merit of the algorithm. No additional model validation has been used in the study. So whatever you see, it's pure InfoNeat. No plain text, no hybrid approach like combining neural network with template attack, not something like that. None of these possible variants has been taken into account. It is whatever you will see is just pure NEAT without any specific pre-processing on the traces. And the metric to understand if the neural network has been able to attack the target is the guessing entropy and the minimum number of traces to obtain guessing entropy equals 0. With that, let's take a look at this large table. I know it's large. Let me walk you through it. How should I read this table? Let's look at the column at the right-hand side, just far right. You can see the number of traces that one should use to achieve the guessing entropy 0. it is compared to all possible, not all possible, but many of the recent papers that you can see on this slide. Some of them have been published in CHES before. Just comparing these, you can see that the performance is good enough compared to the state of the art. And then next column that I want to show you is the number of epochs. The number of epochs shows how fast the network could converge to the results. And if you give the network more and more epochs, the possibility of having overfitting will be increased. So the sooner you can conclude, the better it would be. And then the next column that I want to show you is number of trainable parameters. That was a nice comment from Trevor in his talk. He mentioned that when we talk about hyperparameter optimization, one would say they are all time consuming. Does it really worth it? Should I just try something and just go for trial and error? It really depends on the number of parameters that you want to train and tune. And if the network is small enough, the cost would be reduced. And as you can see, for the InfoNet, the size of the networks is quite compact. There was also another question and discussion about training on desync datasets. For ASCAD, we know that each of those fixed and variable key cases comes with 2 other desynchronized datasets. And what I'm going to show you is just the reason why training on synced traces and testing on desync traces might be useful. In some cases, alignment is not easy to do. And if the neural network or any machine learning technique can be helped in that regard, it is appreciated. So it means in the training phase, the neural network is tuned and trained by the attacker on an open copy of the device, and it is possible to let's say, train on the synced traces. And now in the attack phase, no retraining is needed, no refinement and fine-tuning would be required. Why is this possible? We have seen examples of this in the literature. We have seen that CNNs can be used in this case. Why it works is just because how the network can see through the traces. It can observe the patterns that, for instance, our eyes cannot follow, but it can capture those patterns and understand that they are relevant, although there is a shift in the data points, but they are all from, let's say, one concept. They are relevant to one another. And why InfoNet can find such features, it is because of its irregular shape. It's not like MLPs. As said before, we are using multi-branching, we are using skipping the branches, and that helps to make irregular neural network. And this irregularity is helpful to just tackle the problem of desynchronization in a very natural way. And how so? I know the graphs are all over the place, but again, let me walk you through it. Except for the graphs in Turkey, all those networks have been trained on desynced traces and tested on desynced traces. Now, just focus on the graphs in Turkey and you see how closely InfoNet can mimic another network that is trained on the same type of traces. So that is one advantage that InfoNet can offer. There are many other results that you can see in the paper. Some of them are quite generalizable. It is not just about applying InfoNet in the context of side channel analysis. For instance, you will see some discussion on how to use learning curves to decide if the model is overfitting or is it just good enough after training. You can see some comments on batch size selection for weight initialization. What are the possible techniques? So you can have an overview of what are possible methods borrowed from machine learning field of study. And on top of that, we have some results on why CMI-based criteria is useful. Without that, what could happen? And then we have also some other results on why one versus all training is useful when you apply InfoNet. And about time complexity of InfoNet, there are some results in the paper, but I would like to also conclude the talk by going through the time complexity of InfoNet compared to its counterparts. What is the closest counterpart of InfoNet? Reinforcement learning. It is not easy to compare them one-to-one because of different ways the big O notation complexity have been formed for these two problems in general in machine learning field of study. But if we just compare the real-time clock and time that we need to train, it is reported in the paper for reinforcement learning. It was shown to be around 4 days for our for the same problem. For InfoNet, half of the time would be enough without any parallelization. I would say parallelization of InfoNet is the next step that we are thinking of, and whatever you have seen is just running that in the easiest way without any specific parallelization. And you have seen we have many neural networks that can be trained in parallel, and that could reduce the time complexity very effectively. What else I can add compared to random search that is very usual in the related works? You could see that InfoNet can convert much faster compared to Bayesian optimization and grid search. We have provided also the big O notations for the time complexity and computational complexity. Thank you for your attention, and I will be happy to take any question. Thank you.
Thank you very much. We have a few time for questions. We have a question right now, right there, please. Here, closer. Yeah.
Thanks for the talk. I'm wondering, so on your last slide, you enumerate the advantages of InfoNet compared to other approaches. Is this specific to the application of search analysis, or is it rather general to any machine learning problem? And if so, why don't we always use this genetic approach?
That's a very good question. Actually, it is in general. So this holds in general, but what we have built is specifically designed for side channel analysis. And how so? One example I have shown here, how 256 submodels have been trained all together, stacked together to make one big, let's say, creator to tackle the problem of side channel analysis. Another aspect is we have chosen the right loss function and output layer for the networks. Also, you can still let them decided by the algorithm itself, So that is one specific aspect of applying InfoNet for side channel analysis. But this holds in general, you're right. And in different applications, it is useful. I don't want to spoil it, but we are using that now for another application. And thanks to very small neural networks that we have, it is a good fit for any problem that should be implemented at the edge. If you have neural network at the edge, you may consider applying InfoNet.
We still have time for one question. Yes, thanks.
Thank you for the talk. I have a question about the initiation of the parameters. About the population, in the paper, you say that you n equals 16 because you have like 16 core, but I was wondering if I have less core and I start like lower, or I have more and I start like with more population, then does it affect a lot to the result eventually?
That's a very good question. Just to give you some context of what the question is about, NEATS comes with its own parameters. There is a short list of parameters that one can tune to let the algorithm run from that point also. So, some of the algorithms are initial values, so they are less sensitive. You can just give it something and it will eventually get to the right point. And because we are making many species, at the end, it will converge to something useful. But the question is about one specific parameters that is relevant to how big the population can be. As said before, we have genomes, we have species, and finally we will get a big population of neural networks that we should choose from. The question is the algorithm sensitive to that parameter? The algorithm itself is not sensitive, but time complexity can be affected by that. Because of that, as said during the talk, if we can parallelize InfoNet, just having many CPUs to run the algorithm in parallel, the better. And then you can increase also the size of the population. And the bigger options that you have, the better you can choose what the CMI-based criteria will work for you. And finally, without any problem, you can choose the best genome out of the big population that you will be.
Thank you.
Okay, unfortunately, we don't have time for more questions, but I think that Seba will be at the coffee break. So if you want to ask her some more questions. So let's thank Seba again, as well as all the speakers of the session. And enjoy the coffee break.